Thank you. Shall we start the class, Sanjay?
Yes, sir, we can start, sir.
Okay. So we just yesterday we had an overview of wing design. We'll go into the integrity details today. So I'll go through main points only because most of it is covered last class. So there are I'm just go through the points where many people tend to make mistakes from my past experience. So in most cases, main lifting wave is single wing. There may be some exceptions to this. Some have tandem wings, some have biplanes. Those are all exceptional cases, and some may have lifting canard. So all those are exceptional cases. So we assume that the wing carries all the weight of the aircraft. Now we looked at how to set the cross-section shape. Now these are the parameters. The average chord length C bar we should know, or there's something called MAC, mean average, mean aerodynamic chord. Then maximum thickness to chord, that is T by C max. So you choose the airfoil with the appropriate T by C. Aspect ratio, B squared by S. B is full span of the wing. If it is semi-span, it is 4B squared by S, but we assume that B is the full span of the complete span, tip to tip. The fuselage comes in between, then also it is tip to tip. So taper ratio lambda is Ct by Cr. Then sweep angle is defined for, so you can define for any line. Usually we call as leading edge sweep. Symbol I think is changing later. It's using the lambda there, he is putting gamma here. So leading edge sweep can be defined, quarter chord sweep can be defined, trailing edge sweep can be defined. These are important points. Trailing edge usually not very common, but leading edge sweep and quarter chord sweep are pretty widely used. These are from aerodynamic point of view. From geometry point, quarter chord is important. From aerodynamic point of view, leading edge sweep is important. That will determine a critical Mach number. And from structural point of view, okay, the maximum thickness wing sweep may be important. That is the sweep at the point where the maximum thickness of the wing happens. For example, at this point, what is the sweep? It may not be quarter chord. It may be okay. One more thing is leading edge radius or nose radius, which we call. This is leading edge sweep. This figure is blacked out, so you are not able to see the maximum thickness line. That will be one more line here. Okay, where there is maximum thickness of airfoil. So it's suggesting the same reference. Here of theory of wing sections by Everton 1.9.5. We are not dealing with leading edge and trailing edge flaps in this section. We'll look at them later during the design. Okay. So after takeoff and landing, we'll determine, at what point the flap should be there, whether you need slats here, all those things we'll decide later. So now this last paragraph is an important one to remember. The ultimate goals for wing design are based on the mission requirements. There is no hard and fast rule. We are given several indications here which may be useful to you. Okay. So generally, you want to have a very high 3D lift coefficient versus angle of attack. That is slope. Okay. That is the slope of the 3D lift coefficient should be as high as possible, which means you may need to have the as high an aspect ratio as possible. This is one of the requirement. What they mean is DCL by D alpha for the whole wing, 3D finite wing. Okay. Then high maximum lift coefficient, the CL max. You want to increase the CL max as much as possible. So choose you want to choose an airfoil which has high CL max. Okay. And you want to choose an airfoil which has high DCL by D alpha, very close to theoretical value, which means a very thin flat plate will have the highest, but we can't have a flat plate. DCL by D alpha. Thin airfoil, remember, camber. Thin airfoil theory will say that the DCL by D alpha is 2 pi. But we can't have that due to thickness and the finite wing. We want to have it as high as possible. So you choose your aerofoil which has as this DCL D alpha as high as possible, then CL max as high as possible, but CD not as low as possible because you don't want the drag to increase. Then a low lift induced drag, which means that K, CD naught plus KCL squared, K also should be as less as possible, which means pi. What does K depend on? K is 1 by pi into aspect ratio into E. So aspect ratio should be as high as possible. These are all our wish list, okay, for a good wing. In addition, you want to have a very high wing volume because if you have a high wing volume, you can the wing you see wing with a high volume with small thickness will have inherent strength of its own. It needs less structure to support it inside from the inside, so you can reduce the structural weight. That is one point. Another one is if you have more wing volume, you can store fuel inside them. So you will have double benefit because of increasing the wing volume. But if increasing the wing volume, unfortunately, the drag may increase. The DCL by D alpha will decrease. So you are in a dilemma. Which one to choose? How much thickness? Okay. So if you have a higher wing volume, the wing weight will be lower. So in some cases, these goals are in conflict and will require some compromises. So finally, you decide what you want. I may tell that I want the best aerodynamic efficient wing, but sometimes you may realize that this high volume or reducing weight is more important for you. So what do? You compromise on your DCL by D alpha or CL max. You put, you know, an extra area for the flap mechanism, increase the CL max. You do something there, but the cost may increase. So you have to compromise here and there. It's just like real life. So this cross-sectional shape, so we've gone through this. DCL by D alpha is 2 pi is KD, okay, 2 pi per radian. So this is the ideal airfoil. Now the angle of stall is alpha as we call. After stall, we'll lose drag and lift. We all know that. An airfoil with small leading edge radius, okay, can have a tendency for leading edge separation at small angles of attack. So what will happen is the alpha stall will be smaller, and your this will lower the CL max also because you are stalling at a lower angle of attack. So you want to increase the leading edge radius because of this one, but this might increase the thickness, and so you may get more drag at other points. So you need to have a compromise. Now the maximum lift coefficient CL max is also affected by T by C max. Look at here, CL max versus the maximum thickness of airfoil. We realize that you get maximum CL max when the thickness is around 14-15%. Okay. 30-50. If you increase also, the CL max decreases. If you decrease it also, the CL max will decrease. Before this, the problem is leading edge separation. After this, it is trailing edge separation. Okay. So from the structural, now, yeah, one more thing. If a laminar separated flow can be induced to reattach through the use of surface roughness. So if you need, you can use all these tricks. Or vortex generators. You might have seen vortex generators on the wing. Okay? These are very small strips which cause the flow of the airfoil surface to become turbulent. So it becomes well mixed and separation is delayed. Then from a structural point of view, there's a benefit to have thicker wing cross section. We have seen this just now. Let's go through this later. So now, as a result of the same amount of bending, this is where the formula, useful formulas come. Your wing weight is proportional to T by C whole power half. Okay, just to give an estimate, root T by C. Okay, but then the weight of fuel carried in the wing. The weight of fuel carried in the wing is proportional to thickness T by C. So this will give you a structural advantage. Okay. We all know what is critical Mach number. I will quiz you on that later, probably in mid some quiz or end some quiz. So we have T by C max versus M critical. Okay. So typically for various Mach numbers, what kind of thicknesses preferred? For low Mach numbers, you can have high thickness without any problem. For high Mach numbers, you have low thickness. Okay. This aerodynamic becomes paramount in higher Mach numbers to increase the critical Mach number. In low Mach numbers, on the other hand, you can have the luxury of having a thicker airfoil. The structural aspect can become important at low Mach because the drag is not a critical criterion at low Mach. Now, historically, these are historical graphs which give you design Mach number versus TVC max. So this is, you can actually choose this graph to make an estimate of the TVC max you need, or you can take it from reference aircraft. You do whatever you feel is correct for your design, right for your design. There are several options here. You choose the options which is best for your design. So you know all this already from previous classes, so I won't go through this. This shows, with increasing camber, the CL alpha curves shift to the left. So alpha naught L is zero lift angle of attack. The increasing camber, the drag bucket shifts to the right. We have CD on y axis and C on x axis. The airfoil shape selection we went to yesterday. We found CL cruise by this formula. Now you can either find the average CL cruise or I told you that the weight may change significantly for long range aircraft. For short range, the weight may not change significantly. So anyway, you find the design CL range, okay, and make sure most of the drag bucket of your airfoil you select falls within the CL range as discussed yesterday. Some airfoils are given here. You can consult theory of inflection for more details. Then 6 series airfoil were actually designed for they were designed for low speed flows, laminar flow airfoils they call. Usually low speed laminar flow airfoils are there. So in World War II times, they wanted laminar flow at higher speeds also. Transonic speeds also. Okay, so they tried to get that laminar flow, but the laminar flow at the they didn't serve that purpose initially. But later on, interestingly, they became the base for. Uh, it didn't survive because of the once it's off design, no, it didn't work. You can design a laminar this 6 series very nicely for a particular Mach number, but if you deviate even slightly, the advantage will be lost, and it becomes worse than other aircraft. So they were not really very successful for Mach numbers less than that. But finally, when people started researching on transonic Mach numbers, they actually found that this gave a good initial design. See, SC, no, super critical Mach number. This is a transonic airfoil. If you see, look at the shape. It is, you know, a large leading edge radius. Then it almost pretty thick and almost straight up to the half chord or more than half chord. Then at the trailing edge, it has a sudden curvature of the chamber, and there is a large. I mean, it becomes thinner at the trailing edge. So this shape is very advantageous for transonic Mach numbers between zero point 0.8 and 1.2. That's why they are called the SC, supercritical airfoils. Okay. Now, 5-digit series is different from 6 series. 6 series also may have 5-digit, but they start with the number 6. Well, supersonic military aircraft likely use NASA 6 series. Accidentally, they discover it works well for supersonic. So now, this is one point you may have to remember, but the thickness should be relatively small for supersonic aircraft. For those who have both a subsonic cruise and a supersonic cruise, you decide which one is more critical or important for your mission, and then decide on the airfoil. Now, how to choose the taper ratio? Generally, for most of the subsonic thing, you take taper ratio is 0.4 because that is closest to a elliptic airfoil approximation. Okay, uh, so people generally tend to use that, but so uh, there is also a figure given 4.1, 4.10. Yeah, so this gives the lambda, which is the taper ratio, versus the quarter chord sweep of a wing. You can make use of this, or you can make use of your, comparison aircraft to get an idea of the taper ratio. Now, how will you say the sweep angle? So, M effective, what is the use of sweep? Sweep increases the critical Mach number of your airfoil. Sorry, the wing. Critical Mach number of the wing. So, if M is the Mach number, the effective Mach number becomes M cos leading edge sweep. Okay. That's how it is important. So, critical also is proportional to 1 by cos cos lambda power m he's telling, but actually, you can say for first approximation, yes, you can say it is 1 by cos lambda. But adding sweep has a disadvantage. So it will actually decrease the wing area. So you have the lift become less. Also, lower effective dynamic pressure will further reduce the lift. Okay, because effective will be Q3 cos squared gamma, and wing weight may increase if you reduce it, if you decrease, if you have C. It is tan gamma power tan squared gamma. You can see wing weight is proportional to tan squared gamma. So large sweep angles will also result in poorer takeoff and landing characteristics because your flaps will be less effective with more sweep is there. So you may need a longer runway length. Okay. So this is one historical figure which shows the leading edge sweep versus Mach number. This this full line. The dotted line just shows you the Mach line, which means that for a Mach number of, for example, 1 or for a Mach number of 2, what sweep will give you a Mach number of 1. For example, if it is 2, cos 60 is half. Okay. So Mach number 2 and the sweep number of 60 will give you a Mach number of 1 at the leading edge of the aircraft. Okay. So the maximum possible Mach number is reached there. If you give a sweep less than that, okay, if you give, for example, only 50-degree sweep, uh, you heard of Mach cone? So if the Mach cone will be just outside the wing for this 60 degrees, the Mach cone is cutting the wing, then you may have shocks and the drag may increase. That is the importance of this leading edge sweep. Okay. So the minimum sweep angle is given here. Gamma is 90 minus sin inverse of 1 by n. That is given by this line. So at Mach numbers greater than 2.4, the sweep angles are historically less than needed to have subsonic flow during leading edge. So we violate this rule more at some higher Mach numbers. This is because the result of the poor subsonic flight characteristic and excessive structural weight that come from having excessively large wing sweep. So you may have to balance here also. If you have aerodynamics as the only goal, then you will be having a problem with structures. So you make a compromise in aerodynamics in some cases. Okay. So you can make use of this figure. Then you have to need a 3D lift coefficient calculation should be there. First, you evaluate DCL by D alpha. What you need here to calculate this is tan of the gamma T by C. That is, you need the maximum thickness sweep. Then you need beta. Beta is root of 1 minus m effective squared, where m effective is m cos leading edge sweep. Okay. And A is nothing but aspect ratio. Okay. So this is the formula to calculate for subsonic Mach numbers. Now, if you get this, units of CL alpha, DCL by D alpha, which you get here, will be in degree power minus 1. This empirical derived, it won't be in radians, it will be in per degree. Okay. Then, so using this slope, you can actually calculate the CL at whatever alpha you want. CL at alpha is 0 plus DCL by D alpha into alpha. So this will also tell you how much alpha you need at cruise. How much the wing should have alpha. The wing alpha, how much should be at cruise, can be estimated from this expression. You have the CL you need at cruise. So with these two, we can tell. Okay, you can go through all this. Should be able to understand. Wing drag estimation is, finally. CD is CD naught plus KCL squared. You can use this K prime CL minus CL min drag, but if you find it pretty difficult, you can leave it because we are not doing a complete design now. We are doing only conceptual design. So K is given by this expression. We used E is 0.8 in earlier weight estimation, but is giving a further refinement for E. See whether it will be useful for you. At this stage, you wouldn't know this D by B, ratio of fuselage diameter wingspan, but you can take it from your reference aircrafts and estimate the value of E more accurate. If you want a better value for E. So it's a reasonable estimate for large range of taper ratios and sweep up. You can use this if you want. How much should be K prime? K prime is here. Third one. If you are using this, then a reasonable range is given here. You have a heavy, very sharp leading edge delta platform. Use this largest value of K. Smallest is very rounded and rectangular platform wing. Depending on that, you can choose the K prime if you are using this expression for C. So if you are using the drag bucket, then this CL minus CL minimum drag will be 0. Okay. So you don't need to worry about K prime in that case. Okay. If your drag buckets falls inside the your usual C. In that range, you can don't have to worry about it. So you can use the parabolic drag pole. Well, now a process is given for the estimating the drag. So you go through this process. Okay, I leave it as an exercise for you. So in this, first you evaluate something called form factor, and there is interference factor known as Q, which is given in this table for various types of wings. You decide what type of wing you want and choose this Q factor. Then CD naught can be evaluated as is CF into F into Q into S wet by S. S wet is wetted surface area of the wing. Okay. Now what is CF? CF is comes from flat plate studies. For laminar flow, CF is given by this expression. Okay. You can approximate this X as wing chord C. If flow is turbulent, then CF is given by this expression. Okay. So you estimate the mean aerodynamic chord of the wing. How will you estimate? You'll come later. So you finish that and come here. Later we'll see, you design the wing before estimating the drag because you need the geometry of the wing to estimate the drag. Okay. This CD naught is base drag coefficient. Then K you'll determine. So for your flight condition, you find out CD naught plus KCL squared. But before you do this, I should tell you, you should determine the plan form geometric relation. Although it comes last, you have to finish this first before estimating the wing drag. Okay. So your wingspan, if you choose the aspect ratio, and these are all interrelated. Okay. Now these equations are given here. You figure out how you are going to make use of these equations. Your wing, when is designed, it should satisfy all these relations. Okay. This is the headache you will have. I leave it to you. I know how to do it, but I won't. It's not worth teaching you. You can actually figure out on your own. Wing aspect ratio dependence is, so all these should be interrelated. Okay, where will you start? You are given relations here. Go through, find out how you start and go about this. Okay, this whole cycle will be a good exercise for you. After this, you freeze on all these parameters. Okay, you need gamma c by 4 somewhere earlier. Tan of gamma c by 4 will come no where here c by c will come. Then quarter chord gamma is also important in some ways. Okay. If you have doubts, you ask me, but don't ask me, sir, what is the process? I leave it to you. You have to explain it in the presentation, the first few groups at least. Okay, so that is you have everything with you. Now design the wing. From tomorrow, can you start the wing loading presentations? Are people ready? So this time we'll start from where will we start? So we'll have the order change a little bit. As I told you, I'll try to distribute the unfairness as fairly as possible. So this time, the groups who presented first, water, bomber, and amphibious. Okay. I want to, come on, I just want to cut this. Insert cut cells. Yes. So this will be the order for the next presentation. First 9, then 11, 14, 2, 5. Okay, like that will be. So regional short haul, Nitin. Nitin, hello? Is Nitin there or something wrong with my system? Are you able to hear me, Sanjay?
Yes, sir.
Ah, nobody seems to answer my calls. So,
Yes, sir.
Nitin, are you there?
Yes, sir. I'm there.
Ah, so who's giving the presentation from your group for wing loading tomorrow?
Sir, we are yet to decide, sir.
Tell me, because tomorrow you are the first group to give. So right now you can quickly. Who else is in your group?
Sir, Shamba, Satyavardhan, and Raj Sirvan.
Shyamla, Satyavardhan, and
Raj Sirvan, sir.
third one I didn't get. Raj.
Raj, sir. Raj.
Raj Sirvani. Okay. So you tell someone they should give. Satyavardhan, are you ready? Can you give Satyavardhan tomorrow?
I'm not sure, sir, 100%.
You don't have to be 100% sure. Okay. If you haven't done anything, you tell what is left to be done. If I know that you are on the right track to finish it off in a week's time, I am okay.
Okay, sir.
Hmm? Okay.
Yeah.
So, or if others are willing, I have no problem. If Raj Sirvani or who's the other one?
Shyamala.
Shyamala. Yeah. Any one of you volunteering?
I can present, sir.
Yeah, sure. So roll number
But I
40.
was
Yeah.
just thinking because I presented the first presentation, so
First presentation doesn't count. That's that is your corporate social responsibility kind.
okay, so then I will
As you
present,
know,
sir.
yeah, yeah. So that's kind of the service you do. No problem. First.
Okay.
This is Shamla.
Roll number
Then
40.
40. Yeah. Military transport. Anyway, we are nearing the time now. We will decide tomorrow for the other groups. Group of 9, 11, 14, 2, 5. Be prepared tomorrow. Okay. Are you able to see the screen?
Yes, sir.
Okay. So the template is set. Military transport.
Excuse me, sir.
Yeah.
Sir, this is Renish. A small request from our side, sir. Can we have the presentations from Monday?
Well, you see, if you keep putting off these presentations, finally there will be a lot of pressure on you during the end of the semester. Already it's going to be good. I mean, I can foresee. Okay, so you are unnecessarily putting pressure on yourself at the last moment when everyone will be pressurized. They will be studying for other exams also.
No, sir. Already we have
Mm.
even other subjects are giving many projects, so that's why.
Now
Just
this will
2 days,
be
sir.
this this
We
this is
can.
this is needs not just 2 days. Next week you are having a long holiday, right? Thursday, Friday, Saturday, Sunday, all 4 days holidays. What am I requesting? You are just presenting whatever you have done. Maybe half of that, maybe nothing. But you tell me how to do it. I want to make sure
Okay.
that you know how to do it.
Okay.
Okay. If you have done something, good. If you have not done
So,
something, tell how you should do it. I
okay.
want to know you understood
So,
how
if
what
the
to do.
final results are not there, also no problem.
No
How we
problem.
are
You tell me.
proceeding? Yeah.
You tell them how you have to do. Okay. The whole class, it's a revision. If I tell, I know, at least 50% of class will be sleeping now. Okay. But when you present, they may not. They may like to hear from you. Okay.
Okay.
Probably you can communicate with them better because you're in the same plane, right?
Okay, sir.
Understand? Okay. Okay. So we'll start from tomorrow. Okay. Then. So let me check the attendance. But report submission, don't miss the deadline. Okay. You have to finish everything by the end of that.
When is that, sir? For wing loading.
Hello? Hello?
For wing loading, when is the deadline, sir?
Tomorrow we are starting. No, tomorrow, what is the date? Thursday, yeah?
13th.
13th. So 20th. 20th is a holiday, but no, you can. It's okay. No big deal. Or you can say, the first working day after that, 20th. When is that?
24th.
23.
23. Yeah, probably 23 evening you can have the deadline, but the deadline for the next one will come very soon. Then that is life. Okay, if you want more time here, then you have to compromise later. You keep on postponing, you'll be in lot of pressure later. You'll see that in your very clearly in this aero design. Better do it on time. The pain will be, you know, you won't get excruciating pain at the wrong moment. That's why I'm telling you. There will be a little pain every week. Yeah, live with it. It will be very good for you. You'll be getting good grades also. If you put off everything till the end, you'll make a hodgepodge finally, and a lot of things can go wrong. My sincere request to you. Okay, so shall we disperse? Have you stopped the recording? Yeah, we have stopped. So thank you. Anything